Welcome. So it is the morning of day 23 of Advent of Code. Um, because last night, I spent a while kind of looking at this problem, but I was tired and wasn't really up for it, so so we're doing it now. And this time, however, I haven't even really thought about this problem last night. I did catch up on at least a little bit of sleep, so maybe we'll enjoy it more. And also, the clock is off, so I can at least take it at a more leisurely pace and try and have more fun, right? So, let's try and remember what we were doing. It's a maze exploration, right? But we had these rules that I, for whatever reason, simply could not understand last night. There are three rules. So let's see if I can grok them now. Never stop immediately outside a room. Okay. Never move from the hallway into a room. What does our sample input look like? It's just the same as that. It's just a different configuration. Yeah. So just 8 thingamabibbies. Never move from the hallway. Stops. Stay in that spot until it can move into a room. You know what? This is not a maze exploration at all. This is a very small graph, because what these creatures are doing, it's not that they're just wandering around. A creature makes exactly 2 moves over its entire life. It has its initial position, it moves to a spot in the hallway, it waits until its destination room is totally empty, or its mate is there, and then it moves to that room. So in fact, and moving to that room when it's empty as soon as possible is always optimal. So the only choice that each creature makes is which spot in the hallway to go and wait, and which creature moves first. And I think which creature moves when, in theory, 8 factorial is the possible number of things, which is a crazy large number, but it's incredibly constrained by who's blocking you. So I think we can just implement that. Move to a spot, implement a move to a spot in the hallway thing. I think we might have to hard code, like in classic programming versus engineering thing. The temptation is, well, what's the general purpose thing we're doing here? If we got some much larger hallway or some larger number of creatures or whatever, how would we do it? And so you're kind of tempted to write some parser that can identify hallways automatic. I mean, I'm tempted right now to write that can detect what the hallway positions are and where the rooms are automatically. But even in engineering, I think that's a terrible idea because we have no idea what the general case of this is. It seems like a very specific scenario, right? So, I guess I'm this is a long way to say I think I'm going to hard code the hallways just as I hard coded these rooms, right? So, um, uh, to, X is 1. And Y is always 1 for all of these things, right? So how many are there? 1, 2, 3, 4, 5, 6, 7. See, the numbers here just don't seem that big. Maybe, maybe the ordering is less constrained than I'm expecting, but it seems like, kind of brute forcing all possible attempts to move is the way to go here. So, 1 and 2, not 3. 4, 6. I counted to 7 wrong, didn't I? I guess that's not a great sign when you can't count to 7. Okay. Okay. 4, 6, 8 are the 3. Yeah, and then 10 and 11. And look at this. I can reuse the 1 in both cases, which will save us a huge amount of time. Brilliant. Oh, not so brilliant. Better. Okay, now we're programming. Okay, so we have rooms, we have... What is this creatures thing I was doing? From character to bool. I think that creature structure is crazy. I don't really know. Oh, look, we had thresholds. We could have... We don't even need the thresholds because we're not moving step by step. Thresholds are always just a way to get where you want to go, right? So, what was I saying? This creature thing, that, let's just get rid of that entirely. Because that's just wrong. Because I think, because that's the only thing that changes. That's our entire state is wrapped up in creatures, right? So let's go. So kind of, I don't think we're gonna need creature. I don't think we're gonna need this all room thing either. I do think our dictionary from creature name to their goal is possibly good. And we always start at the top. Okay. So I think that's going to be useful. So our state is effectively going to be an array of character and point to pairs. That is of length 8, I guess. Okay. So, and what is our, so for each, so I think we can do this recursively because there aren't that many moves. Let's just call it best. Oh no, we'll be Swifty from, and then from the state, right? And actually, should we pass the cost? No, we will return the additional cost. We'll return the additional cost of getting to the end state from, right? And so the total cost will have to sum up all these additional costs to the root of the recursion. Recursion is weird because it has a base, but the base is at the end, and I guess I'm calling the root the thing that's the opposite of the base. Only I can offer this kind of insight into computer science. Okay, so what do we do? So we're definitely going to do something for everything in here. For character and pause in from, right? Now. And for, well, should we know whether, yeah, let's say if calls contains so Oh, and actually, there are lots of states from which we, well, I assume there are going to be states from which we can't get anywhere, right? So, um, is that possible? Whatever. Um, uh, Again, we're not on the clock, so I might as well just chat. We might extend this interface to do what in optimization circles is called like branch and bound, because there might be actually a huge number of ways you can do this. Actually, I'm not sure because we only have one move and then another. Anyway, branch and bound is effectively if you're looking for like the shortest path somewhere, once you have any path, your shortest path so far, if you ever exceed that, you can give up on exploring whatever other paths result after that, right? So I was just thinking we could do that here, but in fact, again, every creature just moves the once and then the second time, so it was just a thought. Anyway, and what you would do is then you would pass a parameter, a second parameter through saying give up if, it costs whatever amount more. But move to the destination room if possible. Otherwise, so how do we tell if we can move to the destination room? So for blocker in. Oop. Oh. So we look at where all the other creatures are. In ba-ba-da-ba-da. Oh, actually, let's because we also want to see if our room is free. So if either of those conditions are not met, then we can give up. Oh, not C. BC. BP. Those look like good variable names. Rooms C contains and let's put that first. Again, this is completely ridiculous, but you should put your cheaper tests first in short circuit things. This makes absolutely no difference for this problem. But just as I'm trying to demonstrate that even though you've seen me write a huge amount of code that was, clearly incredibly wasteful, in real life, I do sometimes understand good engineering practice. It's a thing. Because, even most products that you build, the performance isn't terribly important. But if you're building library code or something, investing huge amounts in tiny little micro optimizations is useful. So, anyway. Then, okay. So we give up if our destination room is not empty, and if we might as well break down the two cases as opposed to doing, because we can be either to the left of our room or to the right of our room, right? So if px is less than c 0 x. So if we're to the left of our room, and and we actually our halls thing, because we don't even need the halls thing, because we could have done whether a position is a hall or, oh, we will need our halls because we're going to loop over that at some point, so that's useful. But I'm going to use halls contains just because it's easier to read, but we could have just done it by Y position, because everything, all the halls are at one Y position, all the rooms are at other Y positions. But anyway, okay, and x, then we're blocked. So we also, so all these conditions could have been chained together in one giant conditional, but again, we're kind of going for readability here, despite the fact that I reordered my tests to be so much faster in the previous conditional. Okay, so we have a clear path to our room, and the room is empty-ish. Okay, so then we just make our move, right? So now we have to figure out which of the two positions we're going to. So hang on. If BC equals C, and so how do they fill up? X, Y. They fill up with the second. Equals rooms C1. So, okay, so rooms C. So we'll try to move to the deepest part of the room, but if we notice another creature in there, then we'll just go there. Okay. There are lots of ways to make this run faster. Among other things, passing all the creatures all the time seems kind of wasteful, because once they're in their room, we can completely ignore them. But whatever. We'll see if we have performance problems. So we're not blocked. So this is entirely deterministic. So we just say yeah, okay, so it's array next state equals hi This is quite an awkward way to do it, but uh, equals P. Then we're going to say that is C dest otherwise 0. I don't know if that's a good or a bad way to update. Okay, so we have updated our state. Cost equals, and it's just the Manhattan distance. So, yeah, because, yeah, we're just going around the block here. So, times, ooh, and we need a parenthesis here, times costs. Okay, so we need that costs array, don't we? I don't know if we need all rooms. We could have made rooms a let variable by just making this a dictionary literal. I might do that because this looks stupid to me, but but it's fine. Okay, so what is they have different energy costs, don't they? Ambers, 1, 10, 100, 1,000. I always had like a thing about programmers should not care about powers of 10. They should always, like as a rule of thumb, use powers of 2. And see, I can't talk and think at the same time. And so I'd always scold my team members when they would round things to power of 10. 10,000? Is it really go that high? No. 1, 10, 100, 1,000. Ah. Also, multiplying by 10 is apparently very complicated for people like me. So, okay. So, we have computed our cost, and this has all been done in a fairly readable way. And now, since this was entirely deterministic, because it's certainly the case that there might be multiple creatures that could move, but if all we care about the cost, it doesn't matter which one moves first, right? So there's no point exploring the different possibilities of who moves first. This is, again, we're pruning our search tree a lot by doing this. So we're not going to explore anything else. We're just doing this and getting it done with. So, if we can actually solve this best return. There's probably a more elegant way to structure that without an if-else, with just doing it in a single expression. But again, these are not terribly important issues. So, if a thing is in a hallway, then this is trivial because it's deterministic. Otherwise, we're in a room, right? And we didn't have any conditionals. Okay, so, sorry, this is our if, right? So how do we know So, let's just try moving to every other hallway and to every hallway position, right? Four. Okay. Well, no, we do have this special case, so we could be in our destination room, and however, we're blocking someone who shouldn't be in our destination room, right? So we should rule, and that requires looking at all the other creatures, right? So we should rule that out. Do, 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 do. Well, well, let's. Okay, 4. Other creature, other position. In. From actually isn't a very good variable name. I maybe should have called it state. I maybe should have called it state because you can actually assign different internal variables than external variables in Swift, which is nice for exactly this reason because it's a poor internal variable but a good calling convention. If what am I doing? If my room contained my position. So if I'm in my destination room, other creature, if other creature is not me, and other and C. If and room C 1, because that's the deeper spot. Then I do need to move. This is all poorly structured, right? Sorry, I'm picking at my lip here. What I really want to do is if I'm not blocking something, then I can just bail out and do another continue because we are where we need to be. So, but at this point we know, so we can just, so again we can bail out. So, oh yeah, so we can, let's not try and get too fancy here. Okay, otherwise, if we're not blocking anyone, then we can just keep going, because we are where we need to be, right? If rooms, yeah, okay, but now we need to try to move. So let's try to move. And this is where we're going to have some branching. Four. Let's add a few more. Okay. I suppose the correct thing to do would be like that. It looks less arbitrary, I suppose. So, fine. And then, because we're going to have branching here, we need to keep track of our best possible branch, right? Or, no, actually. I don't know if it's true that there are unsolvable positions, but we might as well remain open to the possibility because I've coded it up to now, but might not be useful. Okay, so for every position in the hall, we need to see if we can get there, right? So, actually, you know what? If okay, this is our destination room. So if let's do another loop in this to see if we're just blocked in entirely, right? So if we're P y minus 1. So that would mean that we're in the bottom of a room and someone else is in the top of a room. So we're trapped. Then okay, so now we are not trapped in a room. So we don't have to worry about that. The only people who could be blocking us are in the hallway. And this is the same logic we used above, I think, right? For H in halls. And we do this all over again. It's a lot of looping, and there are much faster ways to do this, but like I say, I think we're going to be fine. Oh, did we only do one side of our thing? If P is to the left of our... See? Ooh. Gotta pay attention to this. So if we're to the right of our room, then someone will block us if they're to our left but to the right of the room, right? Okay. So let's actually save. Just reuse both of these because now that we've looked at it, it must be right, mustn't it? Okay. So if we are to the left of where we want to go, and the other guy is actually let's, because we haven't used it yet, blocking creatures. Yes, if we are to the left of where we need to go, and the other guy's in the hall, and he's to the right of us, and he's to the left of left or equal, because he might be occupying it, right? Oh, then continue. This needs to be our Hall loop. Right, and I think I'd rather copy than do the edit again. If we are to the right of where we need to go, and our blocker is to our left, but blocking that position, then we give up on this Hall. So it looks like we can get there. So now we do our move. And where did we do our move before? Let next state. If that is us, then we move to the Hall. Otherwise, everybody else. Cost is the Hall. Cost is that distance there. Okay. Then, new B, then B equals the min of B, and fine. But we're branching here, so we don't just return that. So that's our Hall loop. So B, that's our else from there. Oh no, but we don't actually. We need to hoist that. Right. C loop function. So we need to hoist B all the way up there. Outside of the creature loop. Okay, so our cost is we're not calculating the B plus cost, so we are doing it correctly there. So what are we doing here is best or next best plus cost, right? That looks a little more sensible. Okay, and then we have these, which are not doing anybody any good. And I don't think we need any of this crap, right? Oh no, this is part of our parsing routine, isn't it? So let's move that up. We could have done that by hand as well. There's so little of it. So, have we written all of our code? Is that the whole thing? Just one big, I'm actually going to move this over there because we want to be able to see more of it in kind of a terminal size screen. I mean, it's quite a big function bordering on the size where it should be broken up, but this is a programming contest. And it's largely cut and paste edits. Yeah, so it's a bit of an ugly function. So, we do need to modify this because it's all messed up, isn't it? If it's that, we don't need that. Is okay, that looks better. Now we can do I'm quite curious how much we've gotten wrong here. It's actually running though. Oh, no, it's not. That was just paging all of the Swift machinery into memory. So, okay, so we forgot to okay, we definitely forgot that, and we almost certainly forgot it the last time. Okay. Next best cost. B cost? Let's, as always, you might as well. Why is this so slow to compile? I mean, forget running. It's just really painfully slow to compile. Okay. 0.2. So let's go to 16. All room. Let's not bother fixing that. All this stuff on 16 is wrong. Fine. Cannot using. Aha. 22. Oh. If you're going to build it that way, you got to be a little smarter about it. Then 97. Well, let's go to 30. What is this? Var dest equals rooms C. We know there's a room C. Sure we do. Of course. So room C, we know there's a room C here as well. And okay, that's a bunch of errors eliminated. What more? I don't find room X. That sounds right to me. That was up on 37, wasn't it? Rooms. Oh, I'm still doing it. Most people don't know this, but on the QWERTY keyboard, X is right below S. That's a helpful pointer. So what? Okay. So that's on line 50, which is right here. Optional costs. Oh, yeah, that makes sense. And we're going to do it a second time down here. So that's those. Character. Costs. Okay, how are we doing now? Okay, OC and BC on line 70 and 76. Wait, what? Immutable. Oh, OC was never used. If rare room, if other is where we're coming from. What was this code for again? See, this is the problem with big functions. I don't even understand what this block was for. Oh yeah, if we're blocked in. So it doesn't matter who's blocking us in, right? And this similar, it doesn't matter who's blocking us, right? So, so now this is actually being quite slow. Now I don't know if, let's, from next state. Oh, we have no terminating condition, do we? So, let's just write our base case here. We actually didn't need the label, did we? Oh, yes, we, what? Blah, 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 blah. This is, again, a very slow way to do this, but it's faster than infinity. So, because I still have no idea how slow our expression That's on 107. That's our print, isn't it? Yes. There's gotta be a way, so let's just bang it. Okay, now, I don't know if we're in an infinite loop or we're just being slow. So let's see what our state is. We could write a visualizer to actually, draw the pretty picture, but, I'm not learning much from this, am I? So D is at 9.2, D is at 9.3, C is at 7.3, C is at 7.2, B is at 5.3, B is at 5.3, 0, 1, 2, A is at 3.3, B is at 5.2. So they're all in rooms. They're all in rooms. In this 2, 3, 3, 2, 3, 3, 2, 2. I mean, in these other ones, I see someone in a hallway, but so what are we gonna do here? Let's say and this is gonna kill me because the tuple isn't hashable. Tuples, man. I mean, there's such a half-assed Swift feature. It's just unbelievable how crap they are. Well, no. I mean, I just want to get a sense of the numbers here. We've got to be looping on something because there aren't that many possibilities, are there? Because you got 8 creatures, and each can go to 7 different hallways, right? So, well, but even so, well, I think we're gonna have to, yeah. So, well, you know what? Yeah, no, this is fine. And, see. Oh. Set of hashable states, right? I gotta remember just not to use tuples because they're so terrible at everything. Why do they give us this syntax if it always turns out to be a mistake? Okay. Do if was not inserted. Let's actually. If it's not inserted, oops. Uh, so millions of things. So what are we doing? So fresh dupes, right? So okay, a huge number of duplicates are being explored. The first duplicate explorer is not necessarily the best one. So I think we might have to keep track of the cost and only do a dupe if it is. Well, would simply memoizing this get there? We might. I mean, because I was building this half thinking we might want to memoize it. So. Yes. So. Yeah. Yeah. We don't need that. And now we return in multiple places, though, don't we? So let's. Oh. Okay. So let's find all our return statements. I wonder if this is actually ever executed. I don't think that's possible, but anyway, we might as well. Yeah, and just one more. Oop. Okay. Oh, we might be no, because you can only... So every step does give us progress, doesn't it? Oh. That's quite shocking to me. Oh, but memoization seems to have gotten us. I wonder if that's the right answer. What is the least energy? Yeah, okay. But there are unsolvable states. I might revisit that because I didn't realize that would be possible. But our essential logic works just fine. It's just a matter of there are a lot of ways to get. Yeah, so there are lots of ways to reach the same state. And so what I was saying earlier, there are two ways to optimize this. One is you can optimize from the bottom up, although those terms are always confusing because you can interpret them in either direction. In this case, we're caching the result, right? What I was mentioning earlier is that we could have done this by keeping track of the cost to get here, and then only making the subcall if we had found a shorter way to get there. And that's a terrible explanation. Because what we're doing here is we're making these recursive calls, and we're returning... Where's our function signature? Right? We're figuring out the best way to finish from where we are right now. And our optimization right now is, it might be that we could ask that question for the same state for multiple different places in the tree. And let's not bother doing it again, because it's always the same. It doesn't matter how we got here. The remaining cost is going to be the same. Sometimes, however, even bottoming out at all, we're never going to hit the bottom of our exploration. Well, actually, I don't know if that's true. But anyway, another way to optimize, you could say, if we're making the call multiple times, we only call it from the shortest path or a shorter path than we found before. But in fact, that's not applicable. So memoization is the right... Well, it worked. Anyway, so let's move on to part 2. Maybe part 2 will be trivial. Okay. Diagram. Oh, you discover an extra part of the diagram. Between the first and second lines that contain the... Oh. So... see, if we had hard-coded everything, this would actually be easier. I'm gonna... This is so silly. Okay. Okay, so between the first and second lines of text that contain... Okay, yes, so it goes here, right? Okay. Fine. So we've done that. Oh, did I just... Oh, no. Okay. Yeah, still similar. So we do have a bunch of code changes to make, but the logic is similar. But we were kind of hard coding the first and second bits of the rooms. We need to extend our rooms, yada, yada, yada. It's not so bad. So first of all, we have to remember... just do that, right? Rooms. Let's make this a dictionary literal just so I don't feel so embarrassed about it all, right? Doesn't that feel better to everyone? Yeah. Oh, I could have used my newfound skills at column editing here, but I didn't because that's just who I am. Yep. I'm an inaccurate text editor. So all our rooms are substantially bigger. Okay, X, Y, 4, 5, okay. And let's, just so we feel super smart. Boom! You see that? You see that? Haha, we saved like hours doing that. Okay. So, rooms, halls the same, costs are the same, initial state, 4PC if contains initial state. Yes, so now we've updated our input so that that does things correctly. This is fine. It's just that this from is going to be longer, so that's all right. Rooms contains if CP that is all right, I think. Yep. So, we're getting into it now. So, if we're in a hallway, okay, let's say we want to move all the way in. Rooms. If it's not, okay. If we're being blocked, it remains the same because the 0 we're just using for the X and the X is the same for all these rooms. If so we know that no other creatures are there. Okay. Okay. So there is one of our own creatures in our destination room. Right. So this is and rooms C contains. So equals So what is dest? It's a position. Point 2 of dest x, and the minimum of dest y and bp y minus 1, right? Okay, so what we're doing here is we're saying if we see another creature, let's aim at the spot above it. And I claim that because of all these various invariants, that will still be a position in the room. And yeah, that's my claim, is that this is my claim is that this is correct, is a bit of a non-statement, isn't it? So costs, yeah. Okay. If, oh, hold on. Okay, if another creature is not our type and room C contains other, so if we're in a room and another creature's in a room and y is less than, okay, I think that's good. Oh, this is if we're in any room. And OPY. And I think that works because the only case that the X's are aligned is if we're in the same room. So there are so many redundant ways to express the same thing. Who knows? That might be a bug, but we'll see. Okay. Okay. Is that it? I don't know. Might as well give it a shot, mightn't we? Let's. Oh, not even close. Look at all them errors. Wow. String room. Why is C a string all of a sudden? 41. If CP and from. Oh, rooms? Oh, because we changed our type here. Character to an array of points. Fewer, a lot fewer. Cannot find points. Yeah, that makes sense. Okay. Oh no, something went horribly wrong. Oh, and line 69. Good for us for putting assertions in. Oh, okay, so I didn't think this through. So Move to destination. Okay, so we're in the hallway. Our destination is there. Oh, because we might hit one of our friends, but there's also a thing there. Yeah. If. This is somewhat inelegant because there is a. No, but it was an over aggressive assertion. In reality, we could have probably just deleted it. If. Yeah. Look at those two exclamation marks on either side of that. That's kind of funny, isn't it? Oh no. Oh, that's very troubling. This is very troubling. So we're effectively saying that we got to the end and there were no routes. There was no solution to anything. That doesn't make a whole lot of sense, does it? I kind of need to use the bathroom. How long? I don't have a clock that says, oh, over an hour. I've been taking a long time to do this. I've been taking my time, though, and it's been moderately fun, but I kind of need to take a break. But let's see if we can get this cracked before then. What have we done wrongly? Oh, wait. Dest equals room 0, 1, 2, 3. Okay, that's fine. Let's start off initial state. For. Let's actually start by. Okay. DDCC. DCBA. Okay, that doesn't look completely nutty. So we do have an initial state with 8 things in it. Are there 8? 2, 3, 4 D's. 1, 2, 3, 4 C's. 1, 2, 3. Wait, 1, 2, 3, 4 B's and 1, 2, 3, 4 A's. Okay, that's one of the things. So now let's check our if. Well, that's easier than doing it by hand. CP. Let's make sure that our rooms are appropriate. X 3579. Yeah. 2, 3, 4, 5. Yeah, okay. All those rooms look. Wait, no, it wouldn't be 8, it'd be 16. Would it? Well, yes, 16. Okay. And let's just be sure. D D D D C C C C B B B A A A A. Yeah. Okay. So 1, 2, 3, 4. It is much tighter because there are fewer hallways for them to squeeze into, but. Okay. If not destination equals destination. Oh, I got, yeah. I might have been just getting too fancy with myself, right? No, we're still not there. This is on 129, yeah. Really. So, that was an if. I need a bang, don't I? Let's just make sure this isn't a gaff in and of itself. Okay, so this is the same thing. You know what? I'm fine with the warning. No solution. Less than ideal. So. Okay. We're not done. If we're in a hallway, we just adjust our destination. I like that. Okay, if we're in a room, if we're in our destination room, did I change this? Other. Is it as simple as that? I haven't thought much else through, but that seemed wrong. Because I think we were saying whether they were blocking us, and this is supposed to be a test to see whether we're blocking them, right? Seems to have substantially increased the search space, at least. If not blocking. Oh yeah, because that means we're in our destination, so we're good. Okay. Oh, it's quite slow, so we might need to do something. Oh no, we got there. Okay, so quite slow. I mean, there are a huge number of optimization opportunities here. But anyway. Yeah, okay. So we finished day 23. There's another day I've wasted a big chunk of my morning. I've spent a big chunk of my morning on Advent Code after already kind of spending some time last night, so I won't dwell. I think I'm feeling good enough to make it another attempt at doing it live because we only get 2 days left. So I'll see you later tonight, I guess.